All right, let's get right into it. We all carry these little supercomputers around in our pockets, but have you ever really stopped to think about how the brains of those devices, the actual computer chips, are made? We're going to trace the journey from a perfect digital idea to a real physical piece of silicon.
And that's the big question, isn't it? Engineers start with this flawless digital blueprint. I mean, a perfect map of every single transistor and wire. But how in the world do you take that and actually build it in the physical world? Honestly, it's one of the most insane manufacturing challenges on the entire planet.
You know, the process is the closest thing we have to modern magic. It's this incredible combination of super precise beams of light, really complex chemistry, and physics that operates on a scale so small it's almost impossible to wrap your head around. It's a story of human ingenuity just pushing the absolute limits of what's possible.
So, where does this all start? Well, funny enough, it's not with the silicone. The whole thing begins with creating a template. You can think of it like the master stencil that's going to be used to print the chip's crazy intricate layers, one after another. This stencil has a name. It's called a photomask. Essentially, it's this plate of ultra pure glass that has the chip's design chemically etched onto a layer of chrome. And get this, a modern chip can have dozens and dozens of layers, which means you need a unique, nearly perfect photomask for every single one of them. Making just one of these masks is a huge process all by itself. As you can see, it starts with getting the data ready, then actually writing the pattern onto the mask, followed by a bunch of chemical processing, and finally a super strict quality check. Let's zoom in on that first step, data prep. Okay, so this first step is fascinating. The thing is, the shapes in a chip design, all these complex polygons, are often way too intricate for the machine that writes the mask to handle. So what do? They use special software to fracture them, basically smashing them down into millions of simpler rectangles and trapezoids that the machine can actually draw. So we've got our stencil. Now we get to the part that just completely bends my mind. Using that stencil to print features onto a silicon wafer that are way, way smaller than the wavelength of light you're using to print them. This is the big one. This is the physics problem that should have stopped progress dead in its tracks years ago. See, the industry uses deep ultraviolet light with a wavelength of 193 nanometers. But the tiny features on a new chip, they can be just a couple dozen nanometers wide. How is that possible? It's like trying to draw a superfine pencil line with a thick, clumsy paintbrush. The enemy here is a phenomenon called light diffraction. Basically, when light squeezes through those tiny patterns on the mask, it doesn't just travel in a perfectly straight line. It bends and spreads out. And that causes the image that lands on the silicon to get all blurry and distorted. Sharp corners get rounded off, and thin lines might not even show up correctly. And this right here shows you the problem perfectly. On the left, you've got the crisp, perfect L shape that the designers wanted. But on the right, that's what you actually get printed on the silicon because of diffraction. It's a blurry, rounded-off mess. So a perfect stencil does not give you a perfect result. So what's the solution? Well, it's completely backwards and totally brilliant. If you know the light is going to distort the pattern in a predictable way, why not pre-distort the stencil in the opposite direction? This incredible technique is called optical proximity correction, or OPC. And just look at this. On the left, that's the OPC-corrected mask. It looks bizarre, right? It's got these weird extra shapes, these little hammerheads and serifs tacked onto the corners and ends. And this is the magic part, when light passes through this messed-up-looking mask, the diffraction effects actually cancel out all the distortions, and what you get on the silicon is the perfect L shape on the right. It's absolute genius. Okay, so OPC is amazing for getting the shapes right. But what happens when you try to cram those shapes super, super close together? Diffraction can make them all blur into one big blob. For that, engineers have another trick up their sleeve. It's called double patterning. Instead of trying to print all of those really dense lines at the same time, which is impossible, they just split the job in two. The first mask comes in and prints every other line, like you see there in blue. That leaves plenty of space in between so nothing gets blurry. Then they come in with a second mask, the red one, and print a whole new set of lines right in the gaps left by the first one. It's way more complicated, but it lets them achieve densities that should be physically impossible. All right, with our ridiculously clever stencils all ready to go, we can finally move on to the main event. actually building the chip itself on a thin mirror disk of pure silicon, which is called a wafer. And this is where the heavy lifting happens. This is not a quick process. We're talking about hundreds of individual, meticulous steps repeating over and over again to build the chip layer by tiny layer. It's broadly broken down into two main phases. First is the front end of line, or FEOL. That's where you build the billions of tiny switches, the transistors. Then comes the back end of line, or BEOL. That's where you lay down what amounts to miles of microscopic copper wiring to connect all those transistors together. Okay, so after weeks and weeks in the factory, the wafer is finally finished. It's now holding hundreds, maybe thousands of identical chips. But the raw silicon itself is incredibly delicate. It needs a suit of armor and a way to talk to the rest of the world. And that's where chip packaging comes into the picture. The individual chips, which are called dies at this point, are literally sliced out of the wafer. Each good die is then placed inside a protective case. This whole unit, the tiny silicon die safe inside its casing, is what we usually think of when we say a computer chip. And that package isn't just a simple box. It's doing three absolutely critical jobs. First, it provides all the metal pins that let the microscopic circuits connect to the much larger circuit board. Second, it acts like a heat sink, pulling away all the intense heat that the chip generates. And finally, it's a suit of armor, protecting that delicate piece of silicon from getting bumped, scratched, or corroded. The chip is built. It's armored up and it's packaged. We're done, right? Not even close. Now, it has to pass its final exams to make sure it actually works, and, just as important, to figure out exactly how good it is. Every single chip that comes off the line goes through some grueling tests. First, a simple check to make sure the packaging process didn't break anything. But then comes the burn-in test. Here, they deliberately stress the chip with way more voltage and heat than it would ever see normally. Why? They're trying to weed out the weak ones that might fail early on, a problem the industry calls infant mortality. Now, here's a really fascinating part of the whole process. Even with all this incredible precision, tiny, unavoidable variations in manufacturing mean that not all chips from the same exact wafer perform identically. Some will just naturally be able to run a little faster or use a little less power than their neighbors. The process of testing them and sorting them based on this performance is called chip binning. And this right here explains something you've definitely seen when you go to buy a computer. Why is there a Core i5, a Core i7, and a Core i9? Well, there's a good chance they all came from the exact same wafer. The fastest, most perfect chips get put in the top bin and are sold as the expensive high-end model. The ones that are just a little bit slower get different names and are sold for less money. So there you have it. From a digital blueprint, through a crazy dance of fractured light, pre-distorted stencils, hundreds of chemical steps, and a brutal final exam, a chip is finally born. It is an absolutely astonishing achievement. So the next time you pick up your phone, maybe you'll see it a little differently, not just as a gadget, but as a monument to human ingenuity, built one impossibly small layer at a time.